Hello there. This video is on section 7.4. I'm going to explain how to find integrals using the method of partial fractions. And this method is without using technology. And once again, with these other methods in chapter 7, the integration by partial fractions is not really a method of integration. It's an algebraic technique that hopefully simplifies an integral into another simpler integral that is recognizable from our list of known integral formulas, or something that we can then do more easily than the original integral problem. The idea behind partial fractions is basically how we add fractions, or more specifically, how we unadd fractions. So as an example, I added a couple fractions in this line right here, 2/5 plus 1/2. I get a common denominator and proportionally equal numerators and add them together. That's the standard method for adding fractions. Notice that the new denominator is the combination of the other two denominators, sometimes called the least common denominator. So that's how we add fractions. Unadding fractions is doing this process backwards. So for my unadding fractions example, I started with a fraction, 16/21. And this 21, we're going to break up into smaller numbers, right? So we're unadding this. So numbers that divide into 21 easily are 3 and 7. So I'm going to have some fraction with a 3 and some fraction with a 7. So I've written a over 7 and a over 3 and b over 7 to represent the two fractions that are going to add up, hopefully, to equal 16/21. So combining these things together using our normal algebra skills, we get 7a plus 3b over 21 is the same or equal to 16/21. Since the 21s are the same, I know the tops have to be the same. So I know that 16 has to equal 7a plus 3b. With numerical answers like this example, there are many solutions that can make 7a plus 3b equal to 16. I wrote a couple of examples here, but there are many more if you want to find some more. And just as a example of this, I took the first one where I got a is 1 and b is 3. And so my a over 3 is 1 over 3. My b over 7 is 3 over 7. And that gives an unadding or a decomposition of fractions. 16/21 is equal to 1 over 3 plus 3 over 7. When we use x's, when we use variables instead of numbers, we're not going to have lots and lots of different solutions. We typically only have one solution when we unadd fractions or decompose fractions. And let me show you how that works. I have 6 examples I'm going to share with you in this video, starting with basic and getting more and more complex as we get towards the end of the 6 examples. All right, so let me show you on this first example. We have a big old fraction. We're going to try to decompose that into smaller fractions. You might want to try using a U substitution and noticing that it doesn't really get much simpler when you try it. This is an example where U substitution or W substitution doesn't quite work. It doesn't really get that much simpler. And this is an example of where partial fractions would be really helpful. I don't want to make this video longer by showing you that W substitution doesn't really give you a simpler result. That might be a nice little assignment for you to do to, satisfy that for yourself. Nonetheless, I need to show you how to do this using partial fractions. And the idea is the big fraction, or the big denominator at least, the 21, is broken up into two smaller things. Like the 21 is broken up into the 3 and the 7, because 3 times 7 is 21. So we need to break up this big denominator into multiple parts, in this case 2 parts, where those parts multiply to be x squared plus x minus 2. So how do we find two things that multiply to be x squared plus x minus 2? Well, finding things that multiply to be this is called factoring. That's what all the factoring stuff was about when you practice that in your previous coursework. So we're going to have to factor, you don't factor the bottom, just factor the top. And this is going to be good practice for some of you. Some of you are just really good at factoring, and you're going to see the answer here. I need x and x, so they multiply to be x squared. I need 2 numbers to multiply to be -2, and somehow all of this mess ends up having a result of positive x in there. So you can try, the only things that multiply by -2 are 1 and 2, or one of them is negative, one of them is positive. It turns out that this pair with a -1 and a +2 works well if you multiply these out. So a little check over here. If I do x - 1 times x plus 2, I multiply x times x times 2, 1 times x, and -1 times 2. And I collect those two middle terms because they're alike. 2x minus x is 1x. And then I get a -2. And hopefully you can see that that's the same as what I started with. So I'm just verifying that this is the correct factorization. Factoring is ultimately a method of guessing and checking. Those who can factor very quickly, it comes down to they can guess and check very quickly in their minds. You may have some shortcuts and rules that help you, but there are no rules that work for all polynomials to be factored. So you always have to know to check. So I'll talk about some more harder ones to factor a little bit later in the examples. Nonetheless, I forgot my dx. Nonetheless, I have factored the denominator, which is going to be your first step in partial fractions simplification. So now we're going to write this into two separate fractions. We got our x - 1, and we got our x plus 2. Those are the two denominators. And I don't know what we're going to put on the top, so I'll just put an a up here and a b up here, sort of as placeholders for whatever we need there to make them add up to the x plus 5 over the x - 1, x plus 1. To sort of have more space to work on this, I'm just going to sort of write the x plus 5 over the x - 1, x plus 1 over here. I'm not going to include the integral yet. I'm going to sort of do some work in the middle. And then when I figure out the correct decomposition, I'll bring back the integral. I'll just fill in my new simplified form when I do the integral. All right, so to be able to solve this, we're just going to have to combine these algebraically. Make some more space. So to combine these algebraically, I have to get a common denominator, which is going to be in my x - 1, x plus 2. And to make the bottom here the same, I have to multiply it by x plus 2. So I proportionally multiply the top by x plus 2. And I get x plus 2 times a. And I'm not going to even multiply it out, and you'll see why in a moment. That's that top right there. And then I get a plus another fraction with the same denominator. Same denominator is going to be x - 1, x plus 2. To get this denominator the right way, I have to multiply by x - 1. And if I multiply the bottom by x - 1, I have to proportionally multiply the top by x - 1. And I'm going to get, well, b times x - 1. Again, I don't really need to multiply it out. And remember, this is equal to x plus 5 over x - 1, x plus 2. And since these two fractions on the left have the exact same denominator, I could just put them all over the same denominator. So I'm going to sort of skip a step in a way and just kind of extend this all the way and say plus, and just get rid of this part right here. So remember, they're both added up over one common denominator. So just like the thirds and 3/7, just combine them together into one denominator. Okay, so that's our just standard algebra of adding fractions. Okay, so we have the denominators, the bottoms are the same. We did that by design. So that means the tops have to be the same. This top here has to equal this top here. So I know that a x plus 2 plus b x - 1 has to equal x plus 5. In order for this decomposition to actually come out correctly, that must be the case. So it seems like we have lots and lots to solve here. I just want to remind you that a and b are fixed. They're constant. They're not going to change. But x is a variable. I know x is a variable because this is an integration problem, and dx says the variable is x. So this equation has to be true for a value of A and a value of B, but it has to be true for all values of X, right? So let me write that down just to emphasize that. So this must be true for all values of X. Because X is a variable and we need this equation to always be true, whether X is 1 or 2 or 5 or 10, we need this equation to always be true. Well, we're going to take advantage of that by making a table. I'm going to put in some X values and figure out what equation I get. But I'm going to be a little bit smart about using X values. I could use X equals 0, X equals 1, X equals 2, X equals 3. I could just label or just roll off a bunch of X values that are convenient, and that will definitely work. So if you just like to just not even think about it and use just a few X values, again, that's fine. It just is going to end up making a little more algebra for you, but it will get you the right answer. What I'm going to do is I'm going to choose X as -2 as my first choice for X, and I'm going to choose X as +1 for my next choice for X. So I'm going to choose two values for X, -2 and 1. And if you think about why I'm choosing those values, you might realize that -2 will make this first term A times 0, which will disappear and make my algebra way, way easier to do. And X equals 1 will make the second term disappear because it'll be times 0, which will all be 0, again, making my life much easier to solve. So choosing wisely can save you a lot of algebra work. So let's go ahead and put in X equals -2. I get A times 0 plus B. Remember, X is -2. -2 minus 1 is -3. And remember, X is -2, so we get -2 plus 5 on the right-hand side. So that's my equation when I substitute the value X equals -2. So what do I get? Well, I'll just do to the side so I have enough room for the other one. A times 0 is 0. B times -3 is -3b. And -2 plus 5 is 3. And then I just divide by -3. And I get B is equal to -1. So now I know in my decomposition, B has to have the value of -1. All right, so let's go ahead and see what happens when I plug in 1. Plug in 1, I have A times 3 plus B times, well, 1 minus 1 is 0. And that's equal to 1 plus 5. And if I simplify this, A times 3 is 3A. That's all 0, and 1 plus 5 is 6. So I get 3A equals 6, and I divide by 3, and that gives me A is equal to 2. So now I know that this decomposition that I want to bring into, like, let me use a different color, that I want to bring into like two separate fractions, or decomposition, has to have A 2 over X minus 1 and B -1 over X plus 2. So that's sort of the algebra of deciding how to decompose our original integral into sort of two smaller fractions. So let's write this down. Let's make sure we keep track of everything. So my original integral, which was X plus 5 over, I'll just keep it in factored form, X minus 1, X plus 2. What is that equal to now? Well, that's equal to the decomposition, which is A over X minus 1 plus B over X plus 2, like this. So now we have two smaller fractions to deal with. Instead of some big old square thing and an X plus 5 on the top, all we have to do is integrate these two things, and we can do them separately. We can integrate the 2 over X minus 1 dx and add that to -1 over X plus 2 dx. And these are much easier to do. We can do these with simple substitution and be able to get the answer. So let's finish off this problem with substitution. I'm going to use U is equal to this thing down here, so that I can just have something divided by U and antidifferentiate using my known formula for antiderivative of something over u. I have to get rid of dx, or I have to solve for dx, but in this case, du is the same as dx. So in this first integral, I get the 2, which I guess I could bring on the outside. X minus 1 is u, and dx and du are the same. And the antiderivative of 2 over u, again, the 2 doesn't matter. I get 2 ln u. I'll put the plus c at the end. How about that? I'll put it here just so I don't forget, because I'll probably forget. And we know what u is. U is simply x minus 1. Right? And we get the second part over here. I'll do the second part in green. For this part over here, I need to make a u substitution. I'll do a w substitution so the variables don't get mixed up. I need the bottom part to be simplified, so I'll make that x plus 2. And dw is the same as dx. So this integral turns into -1 over, that whole stuff is w, times dw. And this is, again, just a formula on our sheet, antiderivative of 1 over w. The -1 doesn't matter. I can bring it on the outside. And the antiderivative of 1 over w is ln w plus c. We need to combine those c's together. It's like c1 and c2, right? They could be different constants. I don't know they're the same constant. They're just some random constant. So let me put all this together. Let me get rid of this guy, guys. So I have 2 ln x minus 1 minus ln of w. Well, w is x plus 2. And I'll just say plus some big C at the end, which is the combination of C1 and C2. And that is the antiderivative of our original equation using the method of partial fractions. So just to review real quick about this method, what we first started doing is factoring the denominator to make sure we knew how to break up the bottom of our fraction. And then we split it up into its smaller fractions using placeholders like a and b to represent the tops of those fractions that work out to be x plus 5 when you add it all up. I simplified that using algebra, and I substituted different values of x in to determine the values of a and b. And then I rewrote my integral into this simpler integral. So that's the whole purpose of partial fractions, is to take this complicated problem and simplified it. So I simplified it into 2 smaller integrals, integrated each one using simple substitution, and got the final result. All right, so that's how all of these are going to work. Obviously, there's twists and turns and things that make it more complicated. That's what I'll be showing you in the next several problems. But this is the nuts and bolts of how all of these problems work. Okay, so let's do some more examples of these. So, next example, creatively labeled B. I have 3x plus 1 over 2x squared minus x minus 1. I'll be doing a very similar procedure. The reason why I thought I would do this example is because the bottom is not as easy to factor. You know, there are fewer rules that help with exactly how to factor this. So factoring is definitely one of those things that, you know, you might need to practice a little bit to be able to do these problems. Factoring is essentially a guess and check process. I do know that there has to be a 2x and an x in order for those to multiply by 2x squared. I do know there has to be a 1 and a -1 in order for those to combine together. 1 and -1 don't combine together to give -1x, but that's not necessarily always true. If I do put the -1 over here and the +1 over here, I invite you to verify or to check that when I FOIL this out, I get exactly the expression I have. 2x times x is 2x squared. 2x times -1 is -2x. And then I have a +1x, which combined together give me -1x. And then the +1 and the -1 multiply to be 1. So that's the factorization. The top is like this. And so my decomposition will be into 2x plus 1 as one of the fractions and x minus 1 as the other fraction. I'll use some placeholders. You don't have to use a and b if you don't want to. It's just like common for people to throw an a and b up there. And then what we're going to do is we're just going to combine these fractions together. So this would be a x minus 1 plus b 2x plus 1 over the common denominator 2x plus 1 and x minus 1. Of course, that has to equal this original expression since we're decomposing this, and it's equal to. Because the two denominators are identical, I must have the two numerators equal to each other. So this and this have to be the same. So let me maybe do this over to the side so that I have enough space. So let me write this down. I'll use some other color. So I get to 3x plus 1 equals ax minus 1 plus b 2x plus 1. And then I'm going to choose some values for x. I'm going to choose x equals 1 because that'll make this first part be a times 0, which is kind of nice. The second one, I'm going to choose x equal to a half because 2 times a half, oh no, it has to be negative half, doesn't it? 2 times a half is 1 plus 1 doesn't give me 0. So x would have to be a negative 1/2. I'm going to move it down a little bit. How about that? X has to be negative 1/2 for the other one. If you want to know like what values of x you should be using, and it's not easy to do it all in your head, you just have to say, well, I want that to be 0, right? If you want, where do I put it? I'll put it down over here. If you want 2x plus 1 to equal 0, then just write out 2x plus 1 equals 0, subtract 1 on both sides, divide by 2, and so you don't have to like do all the mental calculations. You can just literally solve it. All right, so for x equals 1, I get 3 times 1 plus 1, which is 4, a times 0, and b times 2 times 1 plus 1 is 3, which gives me 4 is equal to 3b. And that gives me b is 4/3. And then for the second calculation, I get negative 1/2. I can't read my own handwriting, so let me fix that. If I can't read my handwriting, I'm not sure everyone out there watching this video is going to be able to read my handwriting. So let me try that again. So negative 1/2. Okay, so 3 times negative 1/2 is just negative 3/2 plus 1. That's the left-hand side. On the right-hand side, we get negative 1/2 minus 1 is negative 3/2. And then we get, well, this one's going to be 0 because we set it up to be 0. 2 times negative half is negative 1 plus 1 is 0. So this is b times 0. So it's going to go away. Negative 3/2 plus 1 is negative 1/2. And this is negative 3/2 a. Multiply both sides by 2. Divide both sides by negative 3. And I know that a is positive 1/3. So I got my value for b, it's 4/3. And I got my value for a 1/3. So now I can rewrite my integral here using the smaller fractions. By the way, some people are saying, how did you do the negative 3/2 plus 1 equals negative 1/2 so fast? I mean, I'm a math teacher. I've been doing fractions for a long time. If you are really not doing fractions, you can avoid this by choosing a different value of x. You can, instead of choosing x as negative 1/2, you can choose x as 0 or x as 2. And, you know, it'll come out just fine, just a few more steps, but using whole numbers instead of using a fraction. So maybe that would be easier if you would like to do that instead. That's up to you. You get to do you. I would recommend practicing fractions because they are super important and prevalent all throughout mathematics and all the courses that use mathematics. So for you out there who are shy of fractions, the better you get at fractions, the sooner you get better at fractions, the more you're going to feel good about all the different coursework you take related to mathematics. All right, so my original integral, which was 3x plus 1 over, well, I'll just do the factor form again, 2x plus 1 x minus 1 dx. That's going to equal the decomposition into 2x plus 1 and x minus 1. And the thing over 2x plus 1 was a, but we know a is 1/3. This is supposed to say 1/3. Okay, I'll just make this also clear 1/3. Okay, and then the b guy is 4/3. So the one over here, the b, is 4/3. And now I have two smaller fractions to antidifferentiate. I need a little bit more space. Okay, move this over. All right, because I got to put my integral sign, my dx, and stuff like that. I mean, essentially, we're doing the two integrals separately. We're doing the integral of 1/3 over 2x plus 1, and then adding that to the integral of 4/3 over x minus 1. Right, so we're just doing them separately. Two smaller fraction problems, each one pretty easy to do with u substitution, and then combine and add them together, combine them together, and we get our answer that we're looking for. All right, so I'll do my u substitution, get rid of the denominator. That's the complicated part that I can get rid of. Here, du is equal to 2dx, or we get du over 2 is dx. So when I put this back into the formula, I'm going to take the 1/3 out just so I don't get confused. 1/3, and then I get my fraction is 1 over u, and then dx is now du over 2. So I can take my 2 out as well, and I get 1/6 integral of 1 over u du, which is the natural log thing. And similarly, for this dude over here, we're going to do w is equal to x minus 1. And that means dw and dx are identical. So this is a little bit easier to do. And I get the integral. I'll take the 4/3 out this time. 4/3 comes out. Integral of 1 over x minus 1 is w. Dx and dw are the same. So that's when I integrate that. So I'm going to get this guy right here, 1/6 integral of 1 over u, which is ln u. And I'm going to add that to this one right here, which is 4/3 times the integral of 1 over w, which is just 4/3 ln w. And so I have now been able to antidifferentiate these by decomposing them and using a little bit of substitution. I'm running out of space, so let me go over here. I have 1/6 ln of u plus 4/3. Where did the 1/6 come from? Remember, there's a 1/3 and the du over 2, so I took the 2 out. So 3 times 2 is 6. If you're wondering where the 6 came from, it's just 1/3 times 1/2. I have here is 4/3. The antiderivative of 1 over w is ln of w. And I get my wonderful plus c. I do have to put these back in terms of the original variable. So u, I know for my substitution, is 2x plus 1. And then w, according to my substitution, is x minus 1. And then that's the end of the problem. That is the answer to example B. Okay, so hopefully that's starting to make sense for you about how to use this partial fraction decomposition. I'm going to do a little bit more complicated one. Even though I don't have any space to do it, I'll figure that out. C, I'm going to zoom in a little bit and try to figure out spacing issues. C has a bigger thing on the top and a bigger thing on the bottom. In fact, it's an x cubed type of deal on the bottom. So we're going to have to be able to factor that. All right, so here's how we do it. For the x cubed thing on the bottom, you'll notice that they all have a factor of x in them. So this x cubed minus x squared minus 6x can be factored to x squared minus x minus 6. And that thing inside the parentheses can be factored further to x minus 3, x plus 2. So I got 3 factors here, x minus 3, x plus 2. Again, please verify that my factoring is correct. and then let me know if it's not, so I can redo this video with the correct factorization. Hopefully it's correct. I can double check. X times x is x squared. Negative 3x and positive 2x makes negative x. Negative 3 times positive 2 is negative 6. Yeah, that's right, Timmy. All right, so the idea here is we take our big old fraction, 4x squared minus 7x minus 12 over this giant factored denominator. And we're going to break it up into smaller fractions. Notice that there are 3 factors, so we're going to have to break it up into 3 fractions. So you need a fraction for each factor here. And since we have 3 of them, we'll have to use A and B, and let's use C. Even though C is R plus C at the end, we're going to reuse that C for this problem because I think we can keep track of it. So same kind of deal, but more complicated because now we have 3 things and need to add the fractions together. So for this guy here, let me just a little bit of cheating space over here. So this is A. I need to multiply by both of these denominators to get my giant denominator equal to x minus 3, x plus 2. Since this first fraction only has x in there, I have to multiply by both x minus 3 and x plus 2. So this is going to be A. Oh, it stopped. Let me fix that real quickly. I'll pause the video to fix my pen. Okay, so that gives us A times the other 2 denominators. And in a similar fashion, I'm going to have to multiply B by the other 2 denominators. So I get the same common denominator. And lastly, I need to do the same thing with C. And the other denominators are x and x minus 3. And of course, this is equal to the original fraction. And the denominators are now identical. So now we know the numerators have to be identical. So we get this guy here has to equal this monstrosity here. Okay, so let me try some values for x. You can think for a moment about what values of x I'm going to choose. I mean, of course, you can choose different ones, but you can think about which ones I choose to strategically make this easier to solve, to make several things equaling 0 so that I can easily solve for what's going on here. All right, so I'm going to choose x equals 3, x equals negative 2, and x equals 0. Those 3 numbers are going to make several of the parentheses with the x's equal to 0, making my life easier to solve these things. All right, so for x equals 3, remember I have to plug in 3 into the left-hand side and the right-hand side. So 3 goes in here is 4 times 3 squared, or 4 times 9, minus 7 times 3, minus 12. Right, that's the plugging in 3 to the left-hand side. I plug in 3 into the right-hand side, I get A times 0. I get B times 3 and times 5. And then I get C times 0, right? Because this part right here, x minus 3 is going to be 0. So all of the stuff is going to simplify. And now I have to figure out my spacing. So, because I've written over here. So maybe I'll just erase the stuff here and go down a little bit. I think it's my best choice. All right, so what do we get here? We get 4 times 9 is 36. 36 minus 21. So 36 minus 21 is 15. 15 minus 12 is 3. So I believe this is 3. That's 0, and we get 15b, which means that b is 3 over 15, which is 1 over 5. So b, why don't you look like a b? B is 3 over 15, or 1 over 5. B So that's the b value. My next x is going to be -2. Let me do a different color. So -2, I'm going to get 4 times -2 squared is just 4. -7 times -2 is +14. And then I get a -12. And that's equal to, well, here we get a times 0 because the x plus 2 goes to 0. Here we get b times 0 because the x plus 2 goes to 0. And then we get c, and then x is -2. And x minus 3 is -5. So cleaning this up a little bit. Let's see, 4 times 4 is 16. 16 plus 14 is 30. Minus 12 is 18. So 18 here. 16, 26, 30. Yeah, 18. And here I get 0, 0, 0, and 10c. -2 times -5 is 10. And that means c is equal to 18 over 10, which simplifies to be just 9 over 5. And lastly, I'm going to be using my x equals 0. And for that one, when I plug it to the left-hand side, I get 4 times 0 minus 7 times 0 minus 12. On the right-hand side, I have a 0 minus 3 is -3. 0 plus 2 is +2. And then I get b times 0 and c times 0. Hopefully this is making sense to you. I know it's kind of long, and I'm using this big equation up here and just plugging in different x values and writing it down. All right, so what did I get here? On the left-hand side, I have 0 minus 0 minus 12, which is -12. Black, please. There we go, -12. A times -3 times 2 is just -6a. And then I get a bunch of zeros. So if I divide by -6, I find a is equal to -12 divided by -6, which is +2. So I know my value for a. I know my value for c. And I know my value for b. And that way I can write these as 3 separate integrals with the decomposition that I did before. All right, so the rest of it is pretty straightforward. It's kind of almost identical to the problems I did previously. My my work here is a little bit messy because this stuff over here is all from the previous problem. So it's messy. I apologize. I just have a hard time visualizing space, and then I run out of it, and then I don't know what to do. So I make the best I can do. So anyway, so my integral thing, my integral of the big old monster 4x squared minus 7x minus 12 over this this fraction thingy thing, factor thing as x minus 3, x plus 2. That big old thing that if you're wondering where I'm looking at this right here, right? That big old thing is going to equal the integral of 3 separate things, a over x plus b over x minus 3, and then plus c over x plus 2. And the a value we know is 2. The b value we know is 1/5. And the c value we know is 9/5. And I think I'm going to leave this as a little exercise for you to do the u substitution and the w substitution. I've already done a couple of them. It works out the exact same way. The first guy, we don't need any substitution because we know the antiderivative of 2 over x. That's just going to be 2 ln of x. The next one, we make u is equal to x minus 3. And we get 1/5 ln of x minus 3. And then the last one, we're going to make the w is equal to x plus 2. And I'm going to get 9/5 ln of x plus 2. And then our wonderful plus c at the end. All right, and that's the answer to that example there. Okay, so hopefully you're starting to see some common things, some patterns on how these work. I have one more example to do on this page. And it again differs. I mean, I'm trying to make them different and more specifically a little bit more challenging each time. So D is more challenging than C, and I'll show you why. But again, it's going to follow the same kind of process. I'm not sure if I can do every single step for every one of these problems because the video is already getting long, and a lot of the steps are just very, very similar. So let me show you on example D, what's different about it, why I think this is maybe more challenging than the previous one. So here's D. It has a very similar denominator, so we're going to have to factor that. So we have x plus 8 on the top. On the bottom, we have x, which is common. And then we can factor out the quadratic inside the parentheses at the bottom. And the factorization of x squared minus 8x plus 16, we need an x. We need an x. We need two things that multiply by 16. And when you check it, -4 and -4 are the ones that multiply out correctly. So that's the correct factorization. So the reason why this is different is that in the previous problem, we had three different factors, x minus 3, and x plus 2. In this one, we have three factors, but two of them are the same. And so without sort of knowing the procedure, you might think that, oh, okay, well, we got x plus 8, we got x minus 4, x minus 4, and that will be a over x and b over x minus 4 and c over x minus 4. That would sort of be the logical next step. We got three things. I put those, but these two are identical, right? There's no difference between b over x minus 4 and c over x minus 4 because b and c are just random numbers anyway. I can just write this as d over x minus 4 if I add them together. So we're not going to get three distinct fractions this way. So the decomposition is not going to work without three distinct. There are three factors on the bottom, so we need three distinct fractions for this to work out. So what do we do? What do we do when we only get two factors? Well, you might want to think about the fact that this is x minus 4 squared. We can write it like this. So the third factor, we have x minus 4, and the third factor is x minus 4 squared. So those are the three factors. When you have a repeated root, in this case, x minus 4 is repeated, then you're going to have to make that into a repeated denominator. X minus 4 is one denominator, and then x minus 4 squared would be the second denominator. And then from here, the procedure sort of is identical to before, where we have to make this into x plus 8, x minus 4, x minus 4. I'll just do squared there. And then we have to sort of get common denominators. For the a, I need to multiply by x minus 4 squared to be able to get x minus 4 squared. For b, I need to multiply by both x and x minus 4 to give me my x minus 4 squared. And then for my c, I just have to multiply by x because it already has the x minus 4 squared. And when I do that, then they all have the same denominator, x minus 4 squared. Because they all have the same denominator, once again, we know that this top thing here has to equal this top thing here. And then I could just choose different values for x and solve for the a and the b and the c. All right, so normally I would say, well, look, x minus 4, I would choose x equals 4. That would make sense. And then for just x, I might choose x equals 0. Maybe I'll put it over here. But I'll put it over here. I think I can do it. And then, wait, do I choose x minus 4, x equals 4 again? That's going to give me the same equation. So there isn't really a great choice for the other value of x because it's not going to make any of those guys equal to 0 that x equals 4 and x equals 0 didn't already do. So we just choose some other value of x that you want. You could choose x equals 1 or anything you want. It's really, really up to you. Personally, I would choose x equals 5. Why 5? You may ask yourself. Because 5 minus 4 is 1, it just makes my algebra a lot easier when I do 1 squared. If I chose 1, I get 1 minus 4, which is -3. -3 squared is 9. I guess it's pretty much just as easy, but I just try to make my life easier by choosing x values. You can choose any x value you want. You don't have to choose 5 or 4 or 0 even. Just choose any x values you want, and you can work out the a and the b and the c. All right, so if I choose x equals 4, x plus 8 is 4 plus 8. And that's equal to, well, this guy is 0, a times 0. Okay, I need to smoosh this over just a little bit. I get 4 plus 8 equals a times 0 squared is 0. B times 0 is going to be 0. And then I get plus c times 4. 4c, or c is equal to 3. So I know my value of c. And then for the middle guy here, I get 0. So I get 0 plus 8 on the left-hand side. On the right-hand side, I have a. 0 minus 4 is minus 4 squared, which is 16. Then I have a b times 0, and I have a c times 0. And so 0 plus 8 is 8. That's equal to 16a, which means a is 1/2. And then my last thing right here, x equals 5. We'll find my last number, my c, my b, excuse me, I already know c. So I'm going to stick 5 into the equation. I get 5 plus 8 on the left-hand side. On the right-hand side, I'm going to get a times 1, because 5 minus 4 is 1 squared is 1. And then I get plus b times 5 times 1 plus c times 5. So I just plug in 5 or whatever number you want, and I do get that out there. So what do I get here? I get 13 is equal to a times 1, b times 5 times 1, which is 5b, and I also get a 5c over here. So this may look complicated, but remember, we already know that a is 1/2, and we know that c is 3. So we already know the value of a, we already know the value of c. So let's just put those in there and be able to solve the problem for b. So using our values that we already have figured out, we get 13 is equal to 1/2 plus 5b plus 5 times 3. All right, just putting in the values for a and c. And now, I just do my little algebra thing, and I solve for pause the video because my cat keeps meowing at me. Okay, I'm back. So solve this equation any way you want for b. You can be creative if you want. You can just do the standard method if you want. As long as you do the same thing to both sides, it will come out. So for example, I can subtract 15 on both sides. I can sub 15, and I'll get -2 is equal to 1/2 plus 5b. And then example, I can multiply by 2. I can do anything I want on both sides. So I'm going to multiply by 2. And that's going to get rid of my fraction. I'll subtract 1. And then I'll divide by 10. And I get b is -5/10, which is just -1/2. All right, so I can solve for my a and my b and my c. You have to do a little bit more work because, we can't just make everything 0 every time. But it's a very similar process. Put in values of x, solve for your a, b, and c. Okay, so that means my original messy integral, which is this x plus 8 over x minus 4 squared, can be written as 3 separate integrals, a over x, b over x minus 4, and c over x minus 4 squared. And each of those we can just do using our normal u substitution. So let me see if I can write this out. So the integral, I'll do black, integral of this crazy thing, which was x plus 8 over x minus 4 squared dx is equal to like 3 fractions. And we're going to put them all in different. So one's a over x, one's b over x minus 4, one is c over x minus 4 squared. So we get something over x. That's the a part. And then we get our b, which is x minus 4. And then we get our c, which is x minus 4 squared. And of course, we know our a, b, and c. Our a is 1/2. Our b is -1/2. And our c is 3. And so we've taken this big old integral on the left, and we've decomposed it into 3 smaller fractions. Each of these we can anti-differentiate. And once again, I'm not going to go through all the steps, although this one over here is a little bit looking different, but it's still a substitution. So I'll show you the substitution for this guy. I'll do u is equal to x minus 4. And that gives me du is equal to dx, right? The derivative is just the same. And so this integral on the right becomes, I'll take the 3 on the outside, 1 over x minus 4 squared becomes u squared du. And 1 over u squared is just the same thing as u to the -2. And that's our normal, power rule for anti-differentiation. You add 1 to the exponent. And then, so this is going to be 3. -1 plus 1 is u to the -1 over -1. And then there's a plus c at the end, as always, right? So that it ends up being a similar kind of strategy. I'm not going to do the, I'm going to let you guys do the other 2. You probably have an idea and intuition about what it's going to be. This first one over here is going to be 1/2 ln x. You don't have to do any substitution to get that one. This one's going to be -1/2 ln of x minus 4. And then we get plus this guy down here, which I have to put back in terms of x's. So I'm going to get 1/2 ln of x minus 1/2. That's a minus. I know it doesn't look like a minus. It's a minus, trust me. I'll prove it to you. There's a minus. Ln of x minus 4, and then I get plus 3, or I guess 3 divided by -1 is -3. So let me write this as a -3 to combine this together. -3, and then u to the -1 is, what's u? U is x minus 4. So we get x minus 4 to the -1 plus c. It's mostly straight. I know it's leaning a little bit down, but it's there. It's there. That's the answer to this example, this long example where we have a repeated root. So I was trying to show you what happens when you have a repeated root. Okay, take a deep breath because we have 2 more levels of complexity, and then we'll be done with all my examples on integration by partial fractions. Okay. There we go. E and F, last 2 problems. All right, and they do get a little harder each time. Let me explain how I think they're a little bit harder and how it's similar but a little bit different for each of these problems. All right, so E, we have another x cubed thing, so we can factor this as before. So I get 5x minus 2, and on the bottom I have x and x squared plus 1 when I factor that. Okay, so let's see if I can make this. That's bigger. There we go. I think that's the same size. All right, I'm fiddling with this in live, which I shouldn't do. There's a little bit smaller. Okay. So this guy, x squared plus 2, is the correct factorization but x squared plus 1 does not factor anymore. I mean, it factors using imaginary numbers, but we're not doing imaginary calculus. That's later on. Beyond Calc 3, we have Calc 4, which is calculus with complex numbers, but that's quite a ways from here. So this cannot be factored anymore, but it's an x squared thing. So it has a power 2. It has 2 roots, but the problem is they're complex roots, and we don't want to do complex math in Calc 2. It's not going to work for us. It's too much we need to know to be able to do that. So we're going to decompose this. We're going to decompose it into 2 parts like before. X and x plus 2 are the 2 real denominators. And here we're going to have to put an A as usual. And then for the other one, because it's a square, it's not going to be enough just to put B. We're not going to be able to get a full decomposition just by putting a B. So what you want to do is you want to put the lower size polynomial, like x. The only thing lower than x is just a constant. But for x squared, you can have a linear term like bx plus c. So if you can see, x squared is a quadratic, and the thing on top of that is a linear, like mx plus b, but it's bx plus c, because we're using b and c for the unknowns. So if you have an x squared as part of your denominator, one of your decomposed fractions, you're going to have to use a linear thing on the top to be able to do a partial fraction decomposition. So that's the gist of why I did example E to show you what to do in that kind of situation. And the rest of it is really going to be the same. We have to add the fractions together. So A, x squared plus 1, B, x, sorry, x, B, x plus c. And then, of course, over our common denominator. And over here, we have the same denominator, so we know that the top parts, the numerators, have to be equal to each other. And then I just use different values for x. I'm not going to be able to make this guy 0 because it's, a complex thing. Like -1 squared doesn't work. I mean, I can use -1, just doesn't make it equal 0. I can make this equaling 0 by choosing x as 0. So I'll just choose x equals 0 because that's the only easy one. So I'm supposed to be in black. X equals 0. On the left-hand side, we have 5 times 0 minus 2. On the right-hand side, we have a times 0 squared plus 1 is just 1. And here we have 0 times whatever, it doesn't matter, right? 0 times bx plus c, but that's all going to go away. So I have a -2 is equal to a, and that is one of our 3 ABC numbers that we need to figure out. The other things, I'm just going to choose some easy values of x to compute. Like x equals 1, I think is pretty easy to compute. So x equals 1. If I put that in there, I get 5 times 1 minus 2, which would be 3. And on the right-hand side, I have a 1 squared plus 1 is 2, so it's a times 2. And then I get plus 1 times bx plus c, which is just going to be 1x plus c. And working this out, I get 3 is equal to 2a. I wrote this wrong. I don't know if you caught it. B times x, if x is 1, is not x. B times x, if x is 1, is b, right? Because the x is 1. I knew something looked a little shady there. Okay, so we have, in this guy right here, we have x is 1, so 1 times b times 1 plus c. So this is correct now. All right, so I get 2a, and then this guy out here is just 1. So I get 2a plus b plus c. But of course, we know a. We know a is -2. So there's no reason to leave that as a mystery, since we know 2 times a is just 2 times -2, which is -4, plus b plus c. And if you want, you can move it over. That might be helpful. If you add 4 to both sides, we get 7 is equal to b plus c. Okay, I don't have a box it yet, but that's an equation we have now. Unfortunately, we don't know the value of b, we don't know the value of c, So we can't easily find B and C yet. But we'll just put one more number in, and then we'll be good to go. So the one more number, you could choose anything you want. You could choose -1. You could choose +2. I don't know. I'm going to choose -1 just because, I don't know, just because. So the 5x minus 2 would be 5 times -1 minus 2, which is going to be -7. On this side, we get a. -1 squared is 1 plus 1 is 2. And then we get plus x, which is -1, times b times x, which is b times -1, or negative b, plus c. And so -5 minus 2 is -7. This is a 2a, and then this is -1 times minus b, and -1 times positive c. Let's not forget to put the a value in there. A is once again -2. And I can bring the 4, I can add 4 to both sides to get this guy right here. So now I have 7 is equal to b plus c, and I have -3 is equal to b minus c. And you have your old algebra problem where you have two equations, and they have the unknowns. They both have the same unknowns of b and c. And so you just solve those equations together, and you could find out the value of b and the value of c. Many different ways of doing this, solving two equations with two unknowns. Use your favorite method. Some people like substitution. I'm one of those people. Some people like adding the equations together, which works really well in this particular example. There are many ways. If you know matrices, you can use matrices to do it. But this one here, I'm just going to show you the adding version because, like I said, it works out really nicely for this problem. I don't usually do the adding, but if we take these two equations and we add them together, 7 minus 3 is 4. B plus b is 2b, and plus c minus c is 0. So immediately I know b is equal to 2. That's how nicely it worked out by adding these together. It won't always happen that way, but this one definitely worked that way. Since I know b is 2, then I can go back to any of these equations like this one, and now I know 7 is equal to, well, b plus c becomes 2 plus c, and then c is equal to just 5. So I know the value of b is 2, I know the value of c is 5, and originally, all the way back up here, we figured out the value of a was -2. So a is -2, and we got our b and c, and so now we can just decompose this like we have done before. So what do we get? I'll have to write it over here on the side. So my original integral is 5x minus 2 over x plus 1. So let me make a sort of a line here separating all the stuff. And maybe I'll do it in red. So I get 5x minus 2 over this denominator thing is broken up into these two things, a over x. So what's my a thing again? -2. And then bx plus c. Bx plus c. So b is, where did b go? B is 2 and c is 5. So bx plus c, bx plus c over x squared plus 1. Okay, so the integral of this thing dx is the integral of this thing dx. All right, and then we're going to break this up. We're going to break it up into integral of, well, -2 over x. I'll bring the -2 on the outside. All right, this is 1 over x dx. And we're going to take the integral of 2x plus 5 over x squared plus 1 dx. And in fact, we're going to break this up a little bit more just to make it easier to do. We're going to break this up as much as we can. What else can we break up, you're wondering? Well, because 2x plus 5 is over a denominator, I can use the distributive property and write this as 2x over x squared plus 1 plus 5 over x squared plus 1. right? That's just distributing out the denominator x squared plus 1 to each of those numerators. So I'm going to integrate three separate things like this. And all three of these are going to be on your formula sheet. So all three of these we can anti-differentiate. This one, the first one we know is the ln x. The second one, you can bring the 2 on the outside if you want. And this becomes x over x squared plus 1, which is a simple substitution problem. You can try u is equal to, let me use a different color there. Let me suggest using u is equal to x squared plus 1. And then it becomes a very simple substitution problem for that middle guy. And for the last one, I'm going to take the 5 out. And I get 1 over x squared plus 1 dx, which you could do by trigonometric substitution if you have learned the 7.1 material, but it's also on our formula sheet. 1 over x plus, the antiderivative of 1 over x squared plus 1 is one of the standard integrals. It's right here. Integral of 1 over 1 plus x squared is just the inverse tangent of x. So you can use the formula sheet for these types of ones, but you can also practice the trig substitution using x's tangent theta. So I'm not going to write out the solution because I'm running out of space and energy. This one anti-differentiates using the u substitution, and this one integrates just using the common integral tables as inverse tangent. Or if you like to practice, you can use trigonometry substitution and do it that way as well. All right, if you want to see more steps, you can always let me know, and I can show you some more steps. But I'm going to go on to the very last problem, which is the last level of difficulty for these partial fraction problems. All right, so what do we do? What is I think is the hardest version of these? Well, that's this example F. So this example, I have a big thing on the top, I have a big thing on the bottom. Of course, it's really complicated, et cetera, et cetera. What makes this, in my mind, more challenging than the previous problems? And the answer is because the top is bigger than the bottom. This is called an improper fraction. This would be something like if you had like 22 over 7, right? The top is bigger than the bottom. You should be able to simplify this into 3 and 1/7, right? It has a whole number part and then a fraction part. And so this is really an improper fraction using x's this time, but we need to simplify it before we're going to be able to do any kind of fraction decomposition. So how the heck do we simplify big old thing on the top divided by big old thing on the bottom? And the answer is you divide. It's a fraction, it's a division, so we divide these two things. So this is for some of you going back a little bit farther in your pre-calculus memories, you take the bottom thing and you literally divide it into the top thing. You just do our division algorithm, whatever your division algorithm that you learned. There are different ways of doing this. This is kind of a standard way taught in American schools, but some schools teach it differently. Some people have been to different schools. So however you want to do it, you got to divide. I will show you the standard way that's taught. So you have this big thing on the left that's going into the big thing on the right. You basically focus on the first thing. So what do I multiply x squared by to get 2x cubed? And the answer is I multiply by 2x. 2x times x squared is going to get rid of 2x cubed. But of course, I just can't multiply, one thing. I have to multiply everything, right? So I have to multiply 2x times all those guys. That's going to give me 2x cubed. Minus 3x times 2x is minus 6x squared. 2x times positive 2 is plus 4x. And just like any kind of division algorithm, once you multiply, you subtract. So I'm going to take my original problem, subtract off this thing, and see what I have remaining. So 2x cubed and minus 2x cubed, because it's minus, remember minus here, that gives you 0, so I have to write that. I have negative 9x squared minus a minus 6x squared. Remember, it's minus 6, so don't forget your minuses and minuses. So this is going to be negative 3x squared. And I have 14x minus 4x, which is just 10x. And then I bring down, the next thing, right? The next thing you just bring down, that's part of the algorithm, right? The way you divide stuff. Okay. And then I basically do it again, right? So now I look at x squared into negative 3x squared. So I try to find out what goes into that thing. In other words, what multiplied by x squared gives me negative 3x squared? And the answer is a negative 3. So this is going to be minus 3. And then I multiply everything by minus 3. And I subtract and see what I get. So minus 3 times x squared is minus 3x squared, which is by design. Minus 3 times minus 3x is plus 9x. Minus 3 times positive 2 is minus 6. And then I subtract. Minus 3x squared minus 3x squared is 0. 10x minus 9x is just 1x. And minus 2 minus 6 is plus 4. And now there's another x squared. It's too big to go into x plus 4. So I'm done with my division. There's a remainder. This is the remainder. It's what's left over after we do as much dividing as possible. Okay, so what do we do now with this division? Well, we know that the original problem, which was, let me do this in blue maybe, 2x cubed minus 9x squared plus 14x minus 2 over this giant denominator, x squared minus 3x plus 2. This whole thing, if I divide it out, I get 2x minus 3. That's the whole part, like the 3 was the whole part. 2x minus 3 is the whole part. That's the part that actually went in. And then the remainder, the plus part, is x plus 4. And of course, that's still over the denominator, x squared minus 3x plus 2. So this is just like any kind of dividing, simplifying of fractions, but the added complexity of you have x's in there instead of just numbers, right? So it becomes all more complicated when you have a higher level math of all those variables and stuff. So it just takes a little practice and you'll be able to divide these things no problem whatsoever. So that means that the integral of this thing dx is the integral of these things. So I can integrate this part, I can integrate this part, and I can integrate this part. So my big old integral problem, I have now simplified into 3 integral problems. The integral of 2x dx, well, that's just x squared, right? We know how to do this one. So I'll put a green check next to that one. The integral of 3 dx, well, that's just 3x. We know how to do that one. And this right here is our old friend partial fractions, right? So this one here is going to be x plus 4. We have to decompose it. We have to factor the bottom, right? So how do you factor the bottom? X squared minus 3x plus 2 factors to x minus 2, x minus 1. So that is the factored form of this guy right here. And we're just going to decompose this into something over the first factor plus something else over the second factor. And at this point, this is exactly like all the other problems that I did previously, where you're just going to get like the same denominator. So a x minus 1 plus b x minus 2 over a common denominator, x minus 2, x minus 1. Since the denominators are the same for these two, in this equation for these two fractions, then I know that I can set the top here equal to the top here. And I could choose values like x equals 1 and x equals 2, solve for a and b, and anti-differentiate those normally. So hopefully, even with me not doing all the steps to get you the final answer, you understand now the technique for even example F. So when the top is the same size or bigger than the bottom, divide. When you divide, you'll get some whole part, like 2x minus 3, and some remainder part. And so the whole part is just going to be integrating that whole part, integrating 2x minus 3 in this situation. And then you integrate the remainder, x plus 4 over whatever denominator. And you could do that typically just using the normal partial fractions. So I know some completionists out there really want to see the final answer. I can't do it all in my head, but I can roughly give you an idea. It's going to be the antiderivative of 2x is going to be x squared. The antiderivative of 3dx is going to be 3x. And then for the antiderivative of x plus 4 over x squared minus 3x, it's going to be some a ln of x minus 2 and some b ln of x minus 1. And it's going to be a plus c. And we do have to figure out the values of a and b, of course. But once you figure out the values of a and the b, then that's what your answer is going to look like. Okay, well, wow, that was a long video. Hopefully, those examples were helpful in helping you learn how to do partial fractions in all kinds of different levels of difficulty. Please reach out if you have any questions, and I hope you have a very nice day. And hopefully, I will see you again very, very soon.